and welcome everybody. My name is Henning Nies and I'm a research assistant at the Institute for Internal Combustion Engines and Powertrain Systems of the Technical University of Darmstadt. And together with our project partners, Stähle Robot Systems, we would like to introduce to you today the possibilities of a co-simulated test environment with the Stähle driver module and with CarMaker at an engine-in-loop test bench.
So let me start with my presentation. I will not only focus on the co-simulated test environments, but also on development processes, especially in the field of real driving emissions, where our setup with CarMaker testbed and with the Stähle driver module offers great opportunities. I will start with a very short introduction. As I said, I am working at the Institute for Internal Combustion Engines and Powertrain Systems of the Technical University of Darmstadt. And at our institute, we have 6 key fields of research. Our presentation today will focus mainly on methodology and on real driving emissions. But we also have a great focus on electrification and on future emission control and future engine technologies, as well as a great focus and various governmental projects on CO2 neutral fuels. Stähle, on the other hand side, as our project partner, is a private founded company, which is very well known for their autopilot systems, especially as an emission driver on the chassis dyno testbed. But Stähle also offers a very wide range of products and robot systems for various applications at a worldwide customer basis. The content of my presentation today is the following. I will start with a short motivation regarding RDE, real driving emissions, and will then point out the development challenge which comes with RDE. I will present the co-simulated test environment, which we built with CarMaker testbed, with the Stähle driver module, and with the engine-in-loop testbed with a AVL Puma automation system. I will show you some results from this testbed, and I will finish with a short conclusion. So RDE. RDE is a very common topic these days, since the European Commission adapted the homologation process in the legislation. And by then, it is not only necessary to conduct tests on the test bench with the vehicle, but also conduct tests on the public road and measure emissions with these tests. And as you see here in this picture, this brings a very complex and statistical viewpoint to this topic RDE, because you have certain influences such as weather, route, traffic, of course, but of course the driver behavior is another influence, which are very variable and interact in between. So this makes RDE a statistical problem in this case, although it is fixed with certain boundary conditions. And when you look at it from the view of development, it is really necessary to use front-loading approaches to make these influences and RDE influences transparent and to be examined in detail. So what you do is you have your random RDE test, of course, and you try to move it to a test bed where it is repeatable and reproducible, and where you really can focus on your influences and impacts, for example, your driver impact here in a transparent and detailed way. When you look at the development process here with the very well-known V diagram, which is applicable for real driving emissions as well. You start here on the simulating side with a backward simulation, go more into detail with the forward simulation. Here comes the CarMaker into play, in an office version, and then move further on in your development process with adding of hardware to your simulating tools for RDE development or powertrain development. X in the loop test benches are well known, starting with an engine in the loop test bench where the engine is replacing, or a real engine is replacing, the engine model in the system and in the simulation, up to the vehicle in the loop test bench where the car is replaced with the car on the chassis dyno test bench. As I said, our project partner Stähle Robot System is offering a wide range of application for their driving robots for the test benches on the one hand side, but also in cooperation with certain software companies, AVL on the one hand side, but of course also IPG with the implementation of the Stähle driver module in CarMaker. The opportunity of a user of the application of the Stähle driver module is, of course, that you have the same driver module or vehicle input generator for all processes, started from simulating here software in the loop up to the test benches and to the proving ground. This means that you have the same behavior and same performance of your driver, of course. And the Stähle companies put great efforts into offering a very human style, human-like drive styles for their drivers, and focus on a repeatable and very precise driving of the drivers. And that's what we want to show you in the following on our results. But first of all, let me get a little more into detail for the RDE development, because as I said, RDE is a very complex topic with certain use cases which come into focus, not only repeatability and analysis of the certain influences, but also the use case of virtual integration of components for RDE testing, as well as the using of RDE reference cycles for calibration efforts. And at the VKM, we developed a methodology toolbox for this, which is built around AVL model and testbed connect, and which addresses RDE in early development stages with a co-simulating tool chain with certain methodology modules. For example, here in your use case virtual integration, you have the ability to add component models for your hybrid powertrain. You have the possibility to do co-simulating here with hybrid strategies, as well as with engine simulating. And one very important aspect of RDE on the test bench is, of course, the real driving thermal impact on your test bench. And what we use in our presentation and our topic today is, of course, the integration of a real driving scenario with the use of CarMaker. This brings me to the use case of my presentation today. We focus on RDE testing on the engine in the loop testbed with CarMaker and the add-on of Stähle driver module. And what we did is, of course, for the virtual driver, we need a vehicle speed profile on a digitalized road. So we created one synthetic road and cycle with the AVL cycle generator. And we implemented this into the CarMaker environment on the office side, as well as on the testbed side with the add-on of the Stähle driver module, and then moved to the testbed where we applied it on the engine in the loop testbed here. So the detailed focus of this use case is then the repeatability and the analysis, especially of our behavior of the virtual driver, here the Stähle driver module, And Stähle offers the opportunities to add a very different drive style settings and strategies, as well as different shifting behavior and strategies. So we focus on that. And a big focus is, of course, test repeatability on the test bed. So I want to show you some results from Stähle here. These are results from a chassis dyno test bed where 3 robot runs of the FTP cycle are shown here. And you can really see that the repeatability of the 3 test runs is very good, with a very accurate and precise following of the set point profile. And as I mentioned before, Stähle is paying high attention onto human-like drive styles of their driving algorithms. So especially on the chassis dyno for emission testing of emission cycles, it's very important to focus on shifting behaviors and pedal behaviors, of course. When you compare the Stähle driver to a wide range of human drivers, you can do so with this diagram. You have the delta throttle integral here, which is a measure for the activity of the driver, so for the pedal activity, so to say, and the delta speed integral here on this axis is a measure for the speed error or speed deviation to your set point profile. And when you look at the Stähle driver here in a very high accurate mode, compared to a wide range of human drivers of this cycle, it comes into focus that the Stähle driver is of mid activity, but offers a very precise driving with a low speed error here compared to the human drivers. We use these measures for the results in the following, but I want to show you in the first step, of course, our test bed setup and our test scenario, which we used. As I said, we are using an engine in a loop test bench with an AVL Puma automating system and with the carmaker test bed as a real driving simulating model here. And the idea of the engine in loop test bed is the following, that you have a closed loop control connection here with the test bed and the simulation, where the pedal behavior of the driver and the set engine speed corresponding to your vehicle speed is put as input values to your test bed. And on your test bed, of course, you do certain measurements. And of course, the measurement of the torque is then guided back to the simulation and is propelling the vehicle in our simulation. What we then did is we used the Stähle driver module add-on, which is available for CarMaker and CarMaker testbed. And you have a graphical user interface here for the Stähle driver module, where you can input all the driver parameters and all the control parameters for your driver. The Stähle driver module is then acting as the main driver, which is driving and controlling the vehicle in the test run. Let me show you the scenario which we used real quick for our tests on the test bed. As we are looking into real driving emissions, we decided to use the VKM commuter route profile, which is a driving profile which is very representative for commuter driving. So you have a trip share of about 60% in urban areas here around Darmstadt. And you have some parts of the test driving on the motorway here and some rural parts, and it is corresponding to the RDE legislation, but in a short route and short profile. Before we used this profile on the testbed, so we digitalized this profile and used it then in CarMaker, but beforehand, We took a look at representative driving behaviors of RDE tests of the vehicle, which we simulated on the test bed later on. And you can see here a very common and very easy maneuver and acceleration up to 50 kilometers per hour with different drivers, but all in the same maneuver. Of course, you have some deviations in the speed profile here as well, but which you can really see is that you have a characteristic accelerating behavior with the interruptions here by the shifting points. But you also see that you have a very, or that you have a certain variance between your drivers here, offering offering a wide scatter band where your different driver styles are located in. And we take this into account for our test bench measurements, which I want to show you here. So we move then to the test bed and tested our commuter route profile. You can see here the velocity profile, urban part, and here driving up to 100 kilometers per hour. And we tested two different driving style setups for the Stähle driver, driver 1 and driver 2, which are, one driver is a very high accurate driver, and one driver is a little softer driver with softer controls. And what you can see on the first hand is, when you look at the velocity set profile here, is that both drivers, although different in the parameterization, both drivers follow the given set profile in a very precise and accurate way. You have some deviations, of course, here in the pedal positions. So the driver act a little different in their pedal actuations, but that's clear because of the different parameterizations. And to really look at these differences here, you can see in this diagram here, as I explained a few slides before, we took a look at two important parameters to describe driving behavior. That's on the first-hand side, RMSSE, which is the root mean squared speed error, which is a measure for your speed error and your deviation, in this case, speed deviation from your set point profile. And we took a look at ASCR, which is the absolute speed change rating, which is in this case a measure for the driver pedal activity. So to say, how nervous the driver is acting on the pedals. And when you look at both drivers, they distinguish in certain ways. Driver 1, for example, has a lower pedal activity, so it is not as nervous as driver 2, but on the other hand side, of course, then has a slightly higher error, speed error regarding the set point profile. And driver 2, as another example, is of course with a slightly lower speed deviation, or driving more accurate than driver 1, but with a higher pedal activity. And this is a very common picture here for the driving styles. So let me conclude this and give you a short conclusion on the results. First of all, RDE, as I shown, is a great challenge in these days, with great variability in the influences and with many interactions. And for RDEs, it is necessary to use front-loading methods with reproducible and in some cases automatable test benches, of course, to focus on the development on the test bench side. And at VKM, we developed a methodology toolbox for this to address various RDE use cases with modular approaches. In this presentation, I showed you that we implemented carmaker testbed with the add-on of the Stähle driver module on the engine in the loop testbed. And this testbed setup shows a great potential regarding RDE testing. I showed you some first results from the testbed. And one important aspect, of course, is that the tests on the testbed are repeatable, that the driver behavior is repeatable. And as I could show you, as that the driver behavior with the Stähle driver add-on is very precise for this use case, and that we have the opportunity here to implement various driving styles and driving parameters to really focus on the driving behavior regarding RDE development. I thank you very much for your kind attention.